Hi everyone, welcome to our video on area and definite integrals, where it's currently highlighted. And what we're going to do with this video is just show where the connection will be to where we left off with integration. So we did a bunch of integration problems in our previous videos, and then now we're moving into area and definite integrals. Well, there'll be a connection really soon, and we're going to slowly get to it, but I wanted to first start with an application where it says a runner's velocity is v of t equals 5 miles per hour. How far did the runner go in 2 hours? And then let's graph v of t. All right, so if the runner is running 5 miles per hour and the runner runs for 2 hours, then we could just multiply. 5 times 2 would be 10. So we should know the runner goes 10 miles. So without doing anything, we know the runner goes, let me try that pin one more time. Okay, so we can answer, let's just underline it. We can answer this right away. So that would be a distance is equal to the velocity times the time. Just to show it with some physics or math symbols. So our velocity is 5 miles per hour. So 5 miles per hour times the 2 hours. And so that the hours just cancel each other out, and we would have 5 times 2 with the miles left over. So it would be 10 miles. Okay, so this is assuming that the runner is running that speed the entire time, doesn't slow down, just keeps going exactly 5 miles per hour. Well, what I want to do with this is show that if we were to graph it, okay, so I'm going to draw this graph. Okay, so this would technically be the v-axis, and this would be the t-axis in this problem. But this is the v is just like y equals 5, which is a horizontal line. Right there, we'll say so. 1, 2, 3, 4, 5. Okay, so that would be just a horizontal line. This is v of t equals 5. And what I want to show is if we're assuming the runner starts at time 0 and goes to, so this won't be to scale, but let's go 1, 2. So here's 1, 2, ran 2 miles. Well, there's a connection between this curve here, the runner's curve, and this area. So from the starting time to the ending time, so we're assuming the runner starts at time 0 and ends at time 2, we know that this area inside of here is the area of a rectangle, which has a length of 5 and a base of 2, which would still be 10. Okay, so it's showing this area matches what we got for the distance. Well, what would carry over for this scenario is if this runner ran at some other function, so the runner slows down, speeds up, so forth, so maybe the runner takes off very slowly and then gets to a constant speed, but then slows down and gets some wind and then slows down again, something like that. Well, still from time 0 to time 2, whatever that would be represented by an area under this curve that would show us a total distance. So what we want to get to eventually is just to say that an area under a curve represents a total. Area under curve represents a total. Okay, so in this problem we use the velocity as our example, but it's true for any other thing. Okay, so if we have a graph and we have a curve, and if we look at the area under the curve between the curve and the x-axis, it would represent a total of something. Okay, and we're going to find ways that we can find this easy, but it's going to take a little time to get there. All right, so just some vocabulary with velocity. So velocity is one of the easiest ones to make this connection with. So given a velocity function of an object, the area under the velocity curve from t equals a to t equals b is the displacement of the object from t equals a to t equals b. So displacement is a variation on distance. So the displacement... The displacement is measuring a distance. Let's write it like this. It is a distance. One difference between displacement and distance. So a distance might be like if I left to the store and I walked 1 mile to it and then I came back to my house, I would have traveled a total distance of 2 miles. Displacement might only say that that's 0 because I ended at the same spot. Okay, so that's why it's a distance. So we're assuming in these cases the runner is running somewhere that's not at the same like final location. Okay, and then for more complicated functions, so this first one was super easy here, where we had the sketch and it was just a quick rectangle and we could just do 5 times 2. So we had that length was 5 and then this length was 2. So 5 times 2 is 10. However, with this second scenario where we made up the velocity is some other thing where we don't know, like it starts off strong and then runs constantly, then gets a little tired, then catches some breath. Well, this is not in a nice shape, but what we do with it is we usually just estimate with a bunch of rectangles. So we'll use these rectangles here, kind of like that, to help us figure out what that actual distance is. Okay, and so some of it will have some errors to it. That's okay, but it still helps us figure out an estimation for what this runner did. Okay, so now I've just continued filling in rectangles. All right, so let's do one example here where we have a picture given, and we'll stick to velocity as our example, but then it will go just to abstract afterwards. So in this example, it says the velocity in feet per second of an object moving along a line is given by v equals f of t on the interval 1 less than or equal t less than or equal to 7, where t is measured in seconds. And then we have our graphs. We're going to divide the interval 1, 7 into n equals 3 subintervals. So the n value really just represents the number of rectangles that we're going to use to make an estimate. Okay, and we can see it in the first one. We see we have 3 rectangles. On each subinterval, assume the object moves at a constant velocity equal to v evaluated at the midpoint. Okay, so let's show, so they just want to say, hey, get that midpoint plotted. So I just put them down. And use these approximations to estimate the displacement of the object from 1 to 7. So we can see there's our starting time, there's our end time, and then we'll repeat the same thing with the more rectangles. Okay, so all this is, so similar to before where we have a velocity function, we want to know the total distance or the displacement that has been traveled. And that we're just using rectangles this time because we have a curve. Rectangle, so curves don't have any specific formula that we use unless it's like exactly a circle. Otherwise, if it's some random curve, we use these rectangles to help us estimate. Okay, and so all we're going to do with this problem is we're going to show that, hey, the base of each of these rectangles from 1 to 3, that's a length of 2. So is it from 3 to 5, so that's also a length of 2. Is the A's kind of in the way. And then from 5 to 7, that's also a length of 2. So we know the base of each of these rectangles is 2. Okay, so we've got the base is 2, and then we have the heights are different heights. Okay, so we can see the height of this first one looks like it's a little bit more than 4. Okay, so maybe like 4.2. Okay, so we have the height of this first one. I'm going to label it right here as 4.2. And then the height of our second rectangle, that looks like it is exactly 6. I might be a little off, but that's okay. It's still okay. So that's 6. And then our last one looks like it's pretty close to 8. I think it's pretty safe to say. Let's just pretend that it's 8. Okay, so we know. So we've got our heights. Okay, so the displacement that we're estimating here, the displacement is the area of each of these rectangles. Let's go ahead and say A1 plus A2 plus A3. So I'm just saying A1 for this first one, A2 for the second one, A3 for the third one. And then while the area of a rectangle is base times height, so let's go ahead and let's put equals over here. So for the area 1, I have a base is 2. And then I have the height is 4.2. And then we have plus for the second area, I have area is 2. And then, or the base is 2, and the height we said is 6, plus the area of the third one has a base of 2, and a height of 8. And then now, what often we will do to help us in these other problems is let's notice that this 2 is common in all terms, so we can factor that. So I'm going to do that in this problem where I take the 2 out, and then we have 4.2 plus 6 plus 8. Okay, so I just factored the 2 out, and this will help us with future ones. Okay, so, and then anyway, all I have to do now is just add this up. It's 18.2 inside the parentheses, so we'd have 2 times 18.2. And then now I can multiply, and we get 36.4. Okay, so that is the displacement for the runner. It was in feet per second, so we're assuming this runner ran about that amount of feet in that time. So this is our estimate. So you can have different answers depending on what your height was for these rectangles, in case you saw it differently, but it is still an estimate. It should be something kind of close to that. Okay, so that's all it is. So the area under the curve, again, is representing some total. This is representing a total length traveled. Okay, and then for the second one, we're going to show with if we have more rectangles, we can kind of assume that it's going to be more accurate, because notice I've got like a big gap here and a big gap there in the first problem, and then maybe too much shaded regions above as well. Whereas these are little tiny shaded regions that are above and little gaps that are below. So we'd assume that this is going to be more accurate. Okay, so our displacement, I'm just going to call it D, would be, we have 6 rectangles. Now, the way I'm going to write this, so let's take our formula from this, is I'm going to write the base, and then we'll just multiply it by the heights of all the rectangles added together. So I'm going to say height 1 plus height 2 plus height 3 plus height 4 plus height 5 plus height 6. Okay, so just taking out the base, and then, well, we can see it looks like the base is just 1 for each of them. 1 all the way through, so that makes this one a little easy. So I'm going to do D equals 1 times the height of all of these. Okay, so let's figure these out. So it looks like the first height is exactly 4. So I'm going to do 4 plus the second one, let's say is 5. I think that's pretty close. Plus the third height, that one does look like it's 6. Plus the fourth height, which looks like it's maybe 6.5. Plus the fifth height, which maybe is about 7.5. And then our last height looks like it's also right at 8. Okay, so these are the heights. Just I didn't label them on all the rectangles like I did the first time because, well, I don't think I would have had enough room. So I was just eyeballing the heights to these, just matching it up with our y-axis. Well, I'll do that for the first 3. So we can see what looked like is 4, 5, and 6. That's why I did 4, 5, and 6 there. And then anyway, well, we'll continue to multiply. So I'm going to leave the 1 until the last step. And then adding this together, however way we think we can do it, in a way that maybe could be done mentally. I don't know. I don't want to try to do it mentally. If you can, that's good. But let's make sure it's correct. So I'm just going to get my quick calculator. 4 plus 5 plus 6 plus 6.5 plus 7.5 plus 8 gives us 37. Okay, so it'd be 37 right here. And then, well, 37 times 1 is going to be 37 feet. Okay, so these are approximations of areas under the curve. Area under curve. Okay, so they are different. It depends on the number of rectangles. They are pretty close. Okay, so one of them, this one's probably a little bit more accurate, the 37. And again, all it does is represent some type of total, which is useful for us when we get to some of the applications. Okay, but for now, that's about it. Let's take a break, and we'll go into other problems that are abstract in the next video. Okay, thanks for watching. See you next time.